looked at my grade before I looked at her. You did a drop. Really wasn't. Genie was like, Martin, like, what's that? I saw you fall asleep. You fell asleep last night with your help. Holy shit. So 700. It's like when you drove last night. It's more fun.
How are you?
Good.
Nice. So let's do some comments about homework.
Sorry.
Yeah, that's okay. And then go ahead with preparing your presentations, which will be next week. So, did you got the email from me like 5 minutes ago? Lift hands if you didn't. Everyone good. Okay, so, everyone, right? So, this is an illustration for problem 1, right? So at the beginning, there are several problems that one can solve analytically, and this one, originally, the idea is that you just solve by pen and paper and give answers. But what if problem is unsolvable? Or you just don't have energy and time? You do it with computer, right? So, do I need to go over the explanation of a problem, or is it clear? So let me probably it's clear for everyone, but I don't hear much enthusiasm. So maybe I'll quickly tell. So this is preparatory step because expansion over basis functions will be used again and again. The problem itself is not so valuable. So the idea is that if you have a function which is ugly in mathematical sense, we still can represent it through good functions. So the idea is that if we add coefficients a0 plus coefficient a1 times cosine 2 by 1 over L times x plus coefficient a2 times cosine 2 by 2 times x over L plus b1 sine 2 pi 1 times x over L plus b2 sine 2 pi 2 x over L, and continue the series by choosing right values for these unknown coefficients. One can obtain any function, any periodic function, even if it has some ugly shape that doesn't have analog in a regular set of functions. And the question is how to find these coefficients. Okay? So there is a property of orthogonality. If you like sines and cosines of different frequencies are orthogonal to each other. So if you multiply this function by, let's say, first of these cosines, cosine 2 pi 1 x over L, and integrate times this function. The integration will kill all terms except this one, and it will be equal to coefficient 1. So, in analogy to our quantum world, this will be an analog of initial wave function, and this will be analog of eigenstate of Hamiltonian. So I'm not telling it is literally these things, but it is analogous, similar. So we need to subsequently take all of these periodic functions with different values of this integer coefficient and convolute them with our function that we want to represent. And by this operation, if you put like arbitrary index k, it will be arbitrary index for the expansion coefficient. Make sense? And same for, since cosines only are not sufficient, one needs to have two sets of functions. Many sines and many cosines. And they will form a complete set. Probably need to use larger font. Is it sufficiently visible? Right. So very soon you will be either writing codes yourself or just modifying existing codes. It is one of the goals of the complicated homeworks is to bring to you to idea that writing codes, even maybe the couple of lines, is so much easier than deriving equations. And probably you have already run the code. You saw what it is, right? So I'm kind of redundantly repeating. So first you define the range, then you define the function, and we can define the step function just as sine of oscillating function. I know that I contradict to myself. Right here we are given the function for these steps, but sine is not among standard list of like trigonometric or polynomial functions. It is either positive or negative. So if we just start running it, you see something. So this dashes shows this oscillatory function, right? Then we do need So integration from plus to minus infinity is not practical. So it will be sufficient to integrate only within one interval. And we did set up in the code that this L size of the periodic cell is just 1. So this red line shows the function only at this limit. And then if you see in this expansion, the first coefficient doesn't have sine or cosine, it is just by itself. So it shows the mean value, average. And if you, if you want to find this coefficient, you just integrate the function over the interval and divide by size of the unit cell. So integrating means the area under the curve, and area under this curve, if it is a box of size 1 and 1, area of this one will be how much?
0.5.
Huh?
0.5.
Yes, 0.5. So if we make it to write it. So it tells, yes, 0.5. And I haven't seen volunteers for numerical integration, but basically you just add together values of the function, multiply by time step, right? So it's integration of the function will give you a coefficient A0. And then one can define the functions, cosine with different period, number, different harmonics, and then one can multiply this cosine by the unknown function and set it up into the coefficient sub k. Then we run it as long as we need. And one can do the same for the sine part of the thing. So if we go to this image, it makes a stop after each coefficient. So this will be cosine with 2 pi cosine, first of these cosines, multiplied by this dashed function, and we need to integrate the area under this curve. So since positive and negative compensate each other, the value for this integration will be 0. So for k equals 1, contribution will be 0. Now if you go to k equals 2, again it will be equal amount, equally proportionated amount of positive and negative parts of the cosine function, right? So it will, they will compensate each other. It will be again 0. For 3 again 0, 4 again 0, 5 again 0, 6 again 0. So if you continue the sequence just according to numerical, this A0 1/2, and this all A sub k will be zeros, right? Give me a little sign if it doesn't sound convincing.
Why is the A sub 0 1/2?
Why A sub 0 1/2?
Now what you're going to pick?
Yes, yes, yes. Because our near-analog function from 0 to L Well, generally, if it should be L over 2. But if you set L equals 1, then you will have. Okay? Yeah, thanks for the question. So, half of a problem has been already solved. Right? You see, it's a little less hectic than deriving equation. And then we go further and scan over sine functions. So in this half period, everything is multiplied by 0, therefore it is not field error. And here it is field error and it is positive, right? So the integral will be not 0 and numerical integration gives 0.3 something. And then we go to the next term, and now it has equal amount of positive and negative, and therefore it is very close to 0. And then if we keep this exercise, we see again something non-zero but smaller, 0.1, then again close to 0, then again something non-zero but getting smaller, and you kind of identifying that even if the terms are non-zero, as far as we go to higher harmonics, they are getting smaller and smaller, right? So this is a justification to, instead of continue for 1,000 terms, just take maybe 5 first terms and then stop. And sometimes one can take even smaller number. Okay, if we look into the code further, so we have obtained the all coefficients, but now we may want to check if we are able to achieve our goal. If we add together all functions multiplied by expansion coefficients, whether we will get the final function, the original function, close enough. So we are adding together zeroth term, average value, and then each of this a and b coefficient times sine and cosine, which is sine and cosine of different harmonics. And at each term, we plotting and waiting until it goes further. So if you have only the first term, so a0, this one, and the first term in front of sine, you see it's already something close. So the sine function plus some offset in y direction already reproduces main features, where it is positive and negative, where it is, right, with the same period. And if you go to next term, it gets a little bit closer to what it should be, right? By adding little wiggles, it approaches, and then approaches even closer. And here we terminate the series. So this oscillatory thing is not quite the meandric function, but it is close enough. So it's a good approximation in here. If you want to make an experiment with the code, you can just modify the size of the cycle consistent at each point. Like here, make summation not to 6, but let's say to 12, 20, or 100. And it is expected that with large enough number of terms, it will reproduce to such extent that human eye will not see the differences. So the value for the overall course is that set of coefficients is discrete numbers, but function itself is continuous. But there is a forward and backward transition between continuous functions and discrete expansion coefficients. They are equivalent to represent the function. Make sense? So I'll make a circle and seeing that you are playing to your happiness with the code. And then I'll make some comments how I would do it analytically. So. Huh? Just click. Without this pauses, it's so quick. Well, right? Give an example of some random function. So,
well, I want to go bigger, go.
I was 400 and then kind of tweaks out for a while.
I did it to 200 and then it went past the mark. Really at one point, I swear. But yeah, it looks pretty good. Oh, now I'm a person. Yeah. Sound hot. 60. No, 50 was better than 60. Talk to each other about some things. Let's try 51.
Finding these coefficients and these finding different ones.
That was the second. This is 0. This is all.
Yes.
Plus the
Let me make a little comment that if you have conflicts with yourself, I may try to resolve it, so you will not. Suppose other engineers in the room. Oh, okay. Suppose you are engineers. Suppose you are electric engineers, and you design digital transmission of voice, right? And suppose you need to, you are military electric engineers, and you need to design secret lines that will not be affected and no one can hear it. So it will have very narrow bandwidth, right? You cannot transmit high quality concert of music, it just commands. So you dissect human voice by, have you ever played with equalizer for music? Anyone? Audio systems, they have like bass, treble, different things. And you can modify whether you want higher frequency or lower frequency more. So if you start singing or telling something, you can tell that acoustic waves are oscillations at different frequencies. And if you sing one like tone, it will be mostly one frequency. If you are whispering or telling something complicated, it will be several tones composed, or if orchestra is playing. Transmitting amplitude of your voice at each millisecond is very expensive. It is much better to find frequency of your voice at this interval of time, transmitted by one number. So during half a second, this person was just telling with one tone. So you just give frequency of these oscillations. And next time it will be different frequency. So there is a way to convert oscillations into just frequencies and amplitudes and transmit it. So this equation is a way to transmit complicated signal as a set of frequencies which are already predefined here, and amplitudes. So if you didn't have conflict with yourself before I started speaking, just ignore. You are fine. But if you had a conflict, maybe this comment helped you to feel better. Okay?
So you find the values for the exponential for less than 6. So up to 6, we can find that.
Oh, you already have it ready to say.
Yeah, I was just writing some.
50 words.
5,000.
Begins hard time here.
There's
Space, the TX, here that is the position is
okay. So
1/100. So
okay.
larger number of
So basically,
number of steps.
so A is so it's just going to take 2 blocks.
At the very top line, there is a L equals 1.
Yeah.
Then TX equals L divided by. So this one is proceeding with this plus.
So when this here solves number 2 for us on home.
Number 1.
Or number 1, sorry, it's the second.
Well, it will be like not full credit, but it will be close to full credit. I'll explain how to get it.
Oh.
Okay? I will find this running the code. Everyone? Okay.
How do you stop a code once it's running?
Huh?
How do you stop a code once it's running?
Who gets the duo computer?
No, like if I put it K to 1 million, and I don't want to go over to 1 million, how do I stop?
Control C.
Control C. Nope. Definitely put 1,000.
So integral from 0 to L, 1 over L, dx. And then function equals, so just f of x. We can split this interval on 2 sub-intervals from 0 to L over 2 dx, and then function is equal 1 on the first half interval, plus 1 over L integral from L over 2 to L. And at this interval function equals 0. Therefore, we can just cancel it, right? So you take integral only on the first half, and then 1 over L integral of dx will be just x, right? X explored from 0 to L over 2. So 1 over L times L over 2 minus 0. Right? Will be equal to 1/2. So we proved that it should be 1/2 here, not L over 2, 1/2. Right? Mathematical proven. A1. 1 over L integral from 0 to L dx cosine 2πx. Again, we split it onto two intervals. 1 over L from 0 to half interval dx cosine plus integral from L over 2 to L cosine dx cosine of something. But we need to multiply it by our function, which is 1 on the first half interval and 0 on the second half interval. Therefore, for second half interval, we just cross it out. 2πx over L. And now we need to practice just integration of cosine. I do hate it, but we can probably get around it. So it would be nicer if the variable here and under differential sign will be the same. So in order to have the same variable, I may, so what do we need to do? I need to divide by L, multiply by 2π. That's it. And to compensate this operation, I need to multiply by L and divide by 2π, right? And now I can tell that it is L here we cancel 1 over 2π integral from 0 to 2 d of new variable du cosine u. Also, if our definition of new variable u equals 2π x over L, then when x equals 0, u equals 0, x equals 0, u equals 0, and when x equals L over 2, u equals π, right? So here our variables go from 0 to π. From 0 to π, du of cosine u, right? So what is cosine, integral of cosine? Is it plus or minus sign? Plus sign. Okay, so it's 1 over 2 π sine u explored from 0 to π. And now we plug in 1 over 2 π sine of π minus sine of 0. What is sine of 0? Huh? 0. What is sine of π? 0. So 0, 0, answer is 0. So the coefficient a1 equals 0, confirmed, right? And then you just repeat the pattern and repeat it 12 times. Well, if I do it on the blackboard, then I should give all credit to myself. if you are lazy, and lazy is a good word, if you're lazy to do stupid operations, you can just put number k here and try to integrate it in general form, okay? And see the pattern. I'll make a circle and make a personal interview if everyone is feeling happy about these little operations. Oh no, don't do this.
Okay.
Yeah.
Hey Alex.
What?
Oh, never mind. I was trying to figure out what's inside the cosine, but it's times by zeros. Never mind.
So we have this.
Oh. Wait, when did we change the limits to zero? Oh. When did we change the limits to zero and yeah, because we added the element two. Yeah.
You only went halfway, so I didn't know if you were like doing a half dab or a
Same
half.
I literally just shows cards where you have one, so you just write see like go here.
Number two is just copy paste of the documents. Or zero, number zero if you have sometimes still want something. Just wait here. Full grade transfer was designed by the partial credit.
Wikipedia, you said an evil word.
Oh, sure. You go to library and open through 50 volumes.
I'm gonna go find an encyclopedia.
For the bees.
Bees like the bee honey?
Yes. For the bees, is there a general way to show it, or should you recommend doing all 6 integrations?
I would do even and odd separately. So because for the even you'll get 1 0, and for odd you can show that you use the pattern.
Okay, so would you just put 2 for 2K?
As soon as you do a couple of times, you will see the pattern and you will be able to. Right now we do have numerical values, but if you integrate, it will be something like I don't know, square root of pi or 3 or whatever. It will be something more definite. Okay, so please play with this one, and if you do, you want me to do same thing for problem 3?
3 or
2
2?
is just copy paste from lecture notes.
Okay.
It's very basic. You already know it. Like for Hamiltonian of free space, solution is plane waves, and energy is p squared over 2m. Right?
Okay.
So it's
That was way back to like lecture 6.
well,
No, I'm saying, but right, that I'm not confusing this with a different topic. That was back in like lecture 6.
I don't. Well, I don't remember was it 6 or 7, but I have an excuse for losing this memory because I didn't need to get credit.
But I'm correct. It's not that far back.
Roughly. Well, you can redo it in 2 lines. Right?
Yeah.
So it's, I assure you, it's not challenging. And even if you skip it, it will not be rewarded with a big credit because everyone understands that it is easy. The credits will be not equal between programs.
This is due Friday, right?
Yes. I'm going to collect and immediately distribute answer key. So if you give me a couple of minutes, I'll prepare some materials and then we'll go over the next problem so you can sit and entertain yourself. And if there will be leftover time after, we'll go over things for presentations.
Oh, I always thought.
Okay, so you just substitute it. Not mine.
Yeah, and then I showed that for all of these.
That's my day today.
It's not that beach.
Were you drinking? All day. I started in the morning.
Because we did that first one.
All my days. I went to high school. I lost 5 points on my exam. So I still got to use it kind of upgrade functions. There should be a lot. The last question was what are the 5 original components of the projects, which I remembered perfectly because it was so basis.
This was the yellow one. Yeah. Of course, the chapter showed we heard this from. You know, yellow page was the guy that was suit that part of the road. Yeah, I think so.
To be fair, I was active. I was bored, so I don't want to leave my class, so I started making it. I started like, okay, well, this actually worked.
That one, fine.
You're gonna be like a civil one and you replace it.
This was the teacher that taught me all the dead baby.
No?
No. Your place that came.
She didn't really.
Oh.
You probably won't. Who the other people here might. That's what we're doing right now. Like this. One's not doing this. Not so much you put my hand here and touch it. This folds. Now all the folds break at once. That makes somebody else broken. Just
Might as well use this.
Is there a second floor? Thanks. No, just like Jason said. Don't want more. Yeah, look at that.
So, it makes one over half inch. I can't go from the store, I have all the things that have all those examples and people spraying them at each other. It's like an invisible barrier. You see those mosquito repellent commercials, all the lots of mosquitoes, it's like that. It's on purpose. Huh? You ever seen that SpongeBob whistle?
Oh, yeah.
Okay, please check your emails if you got something. So give me a sign if you didn't got email. Everyone got it.
I got the email, but it won't open.
It won't open? Anyone else has problems opening? Everyone. Okay, everyone was able to open. Huh? So there should be an attachment.
Try closing that out.
Maybe just show it. So, is it clear what is the question in this problem? No? Not quite? Same thing as in number one. So, you do have your basis function. You have your f of x, which is equals e to the minus x squared over sigma, right? And by, if you would add together these functions, wait. I'm just going too quick. So we do have initial, we do have function, continuous function, this Gaussian shape, right? E0. And Gaussian function is also not a part of standard like sines, cosines, x squared, right? So the question can be encoded in form of sines, cosines, or something else. So there is an expectation that if you add together plane waves, which, and you know this, plane waves, EIKX, is nothing but cosine KX plus I sine KX, right? So it is the same thing. For real part, it's cosines, for imaginary, it's sines. if you add together plane waves times unknown expansion coefficients, then one would be able to reproduce original function with certain precision. Like if we make this very detailed, if we do it in a very detailed way, we will reproduce function really well. If we do it coarse-grained, maybe it will be not as precise. Same as you saw in problem number 1. So how do we do this problem? What is based on? So if you multiply this, so it is based on the fact that plane waves are orthogonal to each other. So integral of e I k x times e I k prime x dx will be 0 if k is not equal k prime, and will be some constant if k exactly equals to k prime. So if we multiply all this expansion by e to the power I k prime x and integrate, all terms except the one where k prime equals to k will be 0. Therefore, so if we integrate, multiply, it will be equal to c sub k. So here I'm repeating it once again. Integral of x times e x dx will be equals c sub k prime. So we just need to practice this exercise. Okay? And then if we know these coefficients, we can plug them back and see if the function is reproduced. In the code that I distributed, the last step is not yet implemented, but time is up, I'll better show the beginning, which you have already practiced. So we start with defining our range for the function, and we define this phi 0 function, right? So if you do new figure, and we can do plot x comma phi. So it is an electron that has been wrapped, localized around the place where formerly there was a proton, localized in space. Now we need to program the plane wave functions. Well, we define imaginary unit, just in case MATLAB has forgotten what it is. We set up some value for the k, and then we just write that it is exponential imaginary unit times k times x. Right? And then if you want to practice this rule, we just multiply this phi k, which is plane wave. I can add here a comment. Plane wave. So we multiply plane wave by our original function, and don't forget, if you reprogram it yourself, period here. Otherwise it will consider them as vectors. If you do want to integrate, we just add together all elements. Summation together multiplied by the offset between near grid points. And then we can repeat it again and again for different values of k, right? So just in case that we understand what we are doing and visualize, there will be a plotting of this plane wave which is assumed to be a spiral, right? Because sine and cosine oscillates. But if we multiply it by Gaussian function, it will be a spiral that is 0 before range, maximum where the Gaussian function is maximal, then going to 0, right? So, real, imaginary, x-axis. If it is high value of k, the fringes will be dense. If it is low value of k, they will be sparse. If the k equals 0, it will be almost no fringes. And there is a little effort to program this k. We go between grid points from maybe minus some number to plus some number, and then multiply the k by size of step in this k space. What is the only difference between our previous exercise with sines and cosines? That there the index of harmonic was always natural, integer. Here in this how we go from Fourier to this Laplace transform to this stuff. In this exercise, the value of k can be any number, can be positive and negative, and can be fractional, right? Because the meaning of the k in the plane wave is the momentum. If there are no potentials, if it is a free particle, there are no speed limits. It can go with any velocity. Forwards, backwards, continuously changing. So we do some grid point spacing, but in fact one can take any value. So if we do run the code, but you know, results of integration are expected to generally must be complex. So this expansion coefficient will have real and imaginary part. Like real of ck plus I times imaginary of c sub k. But in this example, you'll see numerically that imaginary part is 0, or numerically 0, so it will be mostly real. But for sanity of coding, one needs to allow both real and imaginary parts. So if you run it, you see this spiral. And I was doing it kind of in a rush, as you may have observed. So the ranges are not super ideal, but it is kind of a spiral that we talked about, right? So it starts somewhere in negative, ends somewhere in positive. In the middle, the amplitude is maximum, and in between, it makes several coils. So these, we go through negative larger value, and then change the value of k, making them smaller and smaller, going to 0, and finally coming to, and then going to positive and growing. So as we click onto if you want to release it from the pause, it will show the value of momentum, value of k, and value of the expansion coefficient. So for k equals -3, expansion coefficient is this much. If you go further, a little smaller, and expansion coefficient gets bigger. And notice that real part is substantial and imaginary part is negligible, or 0. And if we go through, you see expansion coefficient grows. And if you look on the image, the coil becomes less and less vivid. Instead of like a couple of coils, it makes half coil or maybe 0 coils. And expansion coefficient continuously increases. -3. So now when we have 0, so it shows very few changes here. And for k equals 0, the expansion coefficient is maximal. Now if you go forward, it starts growing. If you notice, coiling starts going opposite side. And then it is same larger value, and then expansion coefficient gets smaller and smaller and smaller and smaller. And then you can summarize how the value of this expansion coefficient depends on the k, right? So it is numerical values of this c sub k. If you type it c k, it will give you table of all values. So if you would be very fearful of math, this could be a like partial credit answer for the homework, right? So make a PowerPoint with this Gaussian bars distribution, give these numbers until the problem is solved, right? Well, it gives some sort of idea how the answer should look like. And we already can interpret it. So the Gaussian function can be reconstructed as a combination of plane waves with expansion coefficients, big surprise, depend on k also as Gaussian function. So we start from Gaussian as function of x, and there we are getting Gaussian as function of k. This is a main observation, right? I'll make a circle and see if you are doing well, and then I'll sit another 5 minutes to perform this operation and reconstruct the original function.
Oh yeah, I was going back to yeah.
You guys enjoyed the quiz?
Yeah, I got to the bar graph. I got to the bar graph.
So I'll just sit in peace and reconstruct the function and then raise the voice again. Okay, I think I'm done, and you may have got enough data of this little script. Right? So everyone got it, right? So please try to run. So first, again, after each operation, it does pause, so that it computes the expansion coefficients, and then it practices this equation of adding together plane waves with the computed expansion coefficients. So it goes through these coils first. And then it shows the original Gaussian function and result of this summation going term by term, starting from negative going to positive. Well, ideally, if I would do it with longer time, I would start adding together positive and negative of the same amplitude at the same time to make it more symmetric. But here's what we get. So first is just, and I'm showing only a real projection because the imaginary, as you will see, will cancel out. So we're adding together. Initially it shows more like oscillations, but then see the central peak of these oscillations get bigger, larger than the side peaks. And it approaches this Gaussian function. So we are not doing it ideally. We have very few grid points in K space, and we do not range them from minus infinity to plus infinity. But approximately, this dashes reproduce the solid line, right? So what we've got, we plug in coefficients into this equation and reproduce original function. Why do we need it? What is the benefit of this operation? The expansion coefficients reproduce our wave function at initial time, and later on, if you remember, they are vital components of our prediction of future. Later on, we merge together these expansion coefficients plane waves times we not here, not in this exercise, not in this lab, but later on we are adding this I h bar energy of plane wave with index k times t, and then it will be time-dependent function. So right now we are skipping it; it's already complicated enough. But if we are in the basis of eigenstates, it is so much easier to add time dependence through this phase accumulation. So it was just a little comment, but in what we do, in the next minutes, we do not have this time dependence. Make sense? So I will make a circle and see if you are happy enough. later on here it's just a little extra. If we convert the C sub k in this, we would have transition functions. This is and so on. If you want to so it is mentioned that part C here there is another definition. You probably didn't large envision because if you go to the end of the video, envision the prospects. So probably you keep healthy curiosity about getting the answer in mathematical form, right? This is truly challenging. So we do, and I will probably go over to write on other part of the board, or maybe on this thing. So C sub k integral from minus to plus infinity minus x squared or sigma naught. If you want to keep typical conventions for Gaussian function, maybe I need to put factor 2, but I do not have energy to write an extra symbol right now. So this is the same as integral dx e to the power minus 1 over sigma naught x squared minus ik times x. So, or we can, we can tell that minus is outside of brackets, and here is just plus between these two terms, right? So we have factors in front of second power and first power. This we can call A, and this we can call E. And now our integral is reformulated, we can redefine. E equals 1 over sigma naught, B equals ik. And then what we need is dx e minus a times x squared plus bx. So if you are in friendship with table of integrals, it's you don't need to be in the era of computers and Wikipedia. They are available in libraries like 100 years ago. It's all integrals that humankind knows, they're tabulated. You just go and find it. And maybe, I don't remember, but little chart with basic mathematical equations that I was distributing, it may have answer to this question. If it does, your problem is solved. Right? Just plug in a smart way. But if you do not have any supporting materials, you can try to solve it by yourself through reducing this integral into the shape e to the minus y squared dy. Okay? So we need to change variables and identify full square in this in the power of exponential, right? Same as we did in class. So this can be thought as square root of a times x squared as our little a squared. Then we need to identify this term in the second term. We write b divided by square root of a, x is natural from here, and then since we want to the square root of a is foreign, so we divide by square root of a, and we also want to have factor 2 in the numerator and denominator. Make sense? So I didn't violate it. It is same thing as it was before. Now, this square root of a times x is my little a. Factor 2 belongs to identification of full square, and b capital divided by 2 square root of a is my little b. So we make dictionary. A equals square root of a times x. B equals b capital divided by 2 square root of a. And then we keep writing. So the c sub k equals integral minus infinity plus infinity dx e to the power minus a squared plus 2ab. Right? But we do want to make it a squared plus 2ab plus 2b squared, right? So no one can resist our wishes. If you want it, we can just put it here. Plus b squared. But if you have our wish, if our wishes are fulfilled, we need to pay for it. So it was e to the power minus b squared, and if you want to keep the correct mathematical construction, we need to multiply it by e to the plus b squared. Right? Then the stuff in the brackets can be rewritten as a plus b squared, right? So c sub k equals integral minus infinity to plus infinity dx e to the power minus a plus b squared, and the factor e to the power plus b squared can be put up front as a coefficient. So we need to change variable of integration to the same stuff as in here. So very soon we will call this a plus b as a new variable, let's say y. And now probably we need to express y in terms of x. capital A times x plus b capital divided by 2 square root of a. Right? Now, if we have derivative of dy equals square root of a dx, and everywhere where we had dx, we can replace it by dy divided by square root of a capital. So we replace dx by dy divided by square root of a. And then our integration, c sub k, will be e to the power plus b squared integral, divided by square root of a, square root of a, dy e to the power minus y squared. Right? From minus infinity to plus infinity. So, through our practice last Friday and this Monday, you identify answer for this Gaussian integral. Dy of e to the minus y squared. So what it is? Yes. Thank you. So your c sub k equals 1 over square root of a e to the power b squared times square root of pi. So the only thing to do is to plug in the values of b squared and a capital and analyze it. Since I really wanted to give you some credit, I will not continue. But when you plug in stuff, you will notice several observations, like b depends on b capital, and b capital has imaginary unit. When you take imaginary unit square, it generates negative. So it will be e to the minus negative something, right? And then it will deal with Gaussian distribution of the c sub k. So c sub k will be Gaussian distribution in terms of index k, in terms of momentum. And if you process it carefully, you will get the answer that you report with glory. So I'll make a circle around to see if you're happy, and then I either complete things or I make some comments about the presentations in not a year and a half, in a week and a half. Yes. Well, you can raise on the fly.
Okay, because I did it, I brought it 6 minutes. Then I worked it.
Yes. Yes.
Okay. Cool. Okay.
For two, just copy paste.
Yep. I was.
For 3, yeah, this is what will come. You just, well, probably it's not well visible, but you can just make sure that you. Makes sense? Yes, this also may be Yes. And then this way. you already know.
I guess,
So probably we all, including myself, are looking forward to complete the session. I'll just, because time is running out, but I'll give a couple of comments about presentations, because we didn't contribute anything to them today. Well, maybe we contributed to the skills of programming. So I especially like this selection. So Alex wants to give concluding remarks and probably to announce adjourn.
I was originally just gonna leave it at that.
Yeah. Well, thank you for leaving free space for me to give introduction. No one selected this three. So derivatives in finding differences, this is really easy. So we can assign it to gauge. Vectors, it's kind of important. Maybe, well, we need either, maybe Ben can do, well, eigenvalues is the hardest and most important things. You can split it between Ben and Caitlin, or give it to Ben as a punishment for not coming here. And then Caitlin can do like dyadic products. But I'm very happy to see vivid votes for programming stuff. So when we kind of covered everything except eigenvalues and the movies, right? So for scripts, for Michael, so what we were doing today, we were doing scripts. So everyone is proficient, you just summarize things, right? And well, this is maybe too simple for one person, but you do concluding remarks.
You'll give me another one.
So we didn't discuss here in class the movies and eigenvalues. So I will focus on these two primarily when we meet next Wednesday, and I will go over the rest if there will be demand. And there will be expectations that in a week and a half, well, in 8 days, like Thursday night before the presentations, you'll submit PowerPoints. And okay, probably enough for today, right? Done, meeting dismissed. I'll stay here a little longer if anyone develops questions.